Yo, what's up, calculus students? We're back outside. The sun is shining. It's a great day. We got Desmos up and ready to roll. We are going to deal with situations where we are given the rate of change of position, but we are unable to go backwards. We do not know the antiderivative of this equation. And even if we did, we now have our access to a calculator or Desmos. Okay. The key to understand is something that maybe we understood in physics, that if you add up your rate of change, your meters per second, over the interval of seconds, you get meters. Meters per second, meters. Or if your derivative is positive, your position is increasing, we can add up, sum up our rates of change, our meters per second over an interval of seconds, and we will know the displacement of position or how much my position goes up. If the derivative goes to negative, we know our position's going down. We will be able to find how much we go down by accumulating the derivative. Or if you want to figure out an ending point and you know a starting point, you can literally not really worry about the sign changes. Instead, you could just accumulate your derivative over the entire interval. Maybe there are sign changes or not. And it will tell you if you go up or if you go down from the first point to the second point. So this is the idea. And again, we are finding what all of our meters per second are per second, like meters per second over the intervals of seconds, meters per second times seconds, meters. So every single time we're going to be doing this, we're going to go to Desmos, we are going to graph, and we are going to look to accumulate. So we're going to graph. We're going to use these multiple times, so I'm going to just save them. We're going to graph it over an interval 0 to 5. So I'm going to go and make this a little bit smaller. Can I make this smaller? Make that bigger. I'm 0 to 5. Good. I can see my velocity is negative until it's 0, then it's positive. So after that, you want a cameo? You want a guest appearance? Yeah, that's what I thought. That's what I thought. Your derivative, you can tell, starts at 0. It's, 0. Going until 5. We got a negative value until, we'll call this A. And then it's positive, which means my position is going to decrease, then increase. Cool. And now we'll accumulate our derivative, meters per second times seconds, find kind of like the area, and that'll tell us how much I'm decreasing and how much I'm increasing. So we will break out our friend, the integral. The integral is the calculator's way of accumulating. And we'll need to find this value A. How we do it is we kind of click on it. We press this button here. It exports the point to the expression list. Let me do that again. You click on this, you export it, and I'm just going to go ahead and say this is A. A equals that. I got to write it down somewhere on my paper. That way I have it. So I have A equals 2.71239. Cool. And if I accumulate my velocities by the split seconds in which we're traveling at those velocities from 0 to A, I get my displacement of position, that my position decreases this much, and might as well hold on to that value. And it's very important for free response, which this test is. You need to write down everything that is calculated. Cool. You'll also need this from A to 5. It's very easy to use Desmos with copy and paste. We can see we go up 4.218. All right, so I'll write that down. This is not sufficient. This is just for kind of my note that from A to 5, I got 4.218. Cool. And now if I want to know my positions at all these times, I have to have my starting position. Well, I start at a position of 3. This is the biggest, like, heads up, guys. This just tells me how much I go up or goes down. You need to know a starting point. You need to like know what the C is. So this is P of 0 is 3. Now, sometimes it's nice to have it up here. P of 0 is 3. And then you do 3 minus 2. So you do 3 plus this. And that gives you the position at time A. So if I were to write this out, this is my position at time A. And then if I take my position at time A and add 4.218, I get 5.141, which is my position at time 5. I'm not doing a good job of that. Sorry, I got to do a better job. Sorry. Free response. My position at time 0 is 3. My position at time A equals my starting position at time 0 plus my displacement, my change in my position, which is 0 to A. I did that and I got 0.922. You could say your position at time B is equal to your position of time A plus your displacement from A to B. I don't know why I said B, I meant 5. You could say start with your position at B. Wow. Position at A. Add your displacement from A to 5, which ends up adding a positive number. This was adding a negative number. So I have this value plus A to 5, and I got this 5.141 value. It should make sense. 3 minus 2 gives me close to 1. 1 plus 4 gets me close to 5. So everything kind of works out. Cool. You could have also done your position at time 5 is equal to your starting position of 3, and then add your displacement over your entire interval. So I could have done this 3 plus 0 to 5, and I would have also had that. Maybe that's going to be the easiest way to do it if we don't want to change our intervals too much. It's up to you. You got to like figure this out and do it yourself. So find the positions at the start and the end of the interval, and find your position at when we change directions. Cool. T sine t plus 1. From 0 to 6. Okay. I have a new A value. That's gone. This is now A. Great. I can see my derivative is stop that. Stop that. See, my derivative is positive until this value, we'll call it A. And then 6 ends right here, so we can see that my derivative is negative until almost 6. If you want to double check, you can plug in x equals 6. You can see, okay, your derivative is negative until 6. Good. So very similar to the last problem where my position is going to increase and decrease. I have my position at time 0 is -4. All right, great. So my position at 0 is 4. My position of A will equal my position of 0 plus my displacement, which is the accumulation of my velocity meters per second times seconds, and then my position at time 6. You can either say it's 4 plus the displacement from 0 to 6, but actually what I would like you to do is find the displacement from A to B. So we'll find the position at A. Now you can do the work and add the displacement from A to B. Cool. For free response, you have to show all this work. For the purposes of like doing these problems, like you do it twice and you're probably fine. And just make sure you're getting it right and you know what you're doing. All right, so we got the velocity. I'm accumulating my velocity from 0 to A. I get 6.433. Accumulating my velocity, meters per second times seconds, meters. Cool. Boom, boom. That's how much I go up. And then we'll go from A to 6 is negative. Makes sense. Negative 6.474. I end up to the left of where I start. Let's go back and do my position of -4. Oops. -4 plus 0 to A is that. And then you could also say what we're about to do, because it's easy to do, is you could say -4 plus how my position changes from 0 to A, and then plus how my position changes from A to 6. You could do that. It's another thing you could do. There's so many options. So I'm like literally going to just copy this and say add how your position changes from A to 6. I'm going to end up just a little bit to the left of where I started because this change is a little bit less than this change. So that checks out. I end up at -4.040. 3 decimal places is what we want. We'll talk about truncating is easier than rounding. Just write the first 3 decimal places and leave the rest off. Okay? Cool. Be careful. What if they give you a position at the end? The position at the end of the interval. Okay, well, we'll talk about it in a second. Let's go ahead and crank this out. Okay, from 0 to 5. Again, why do I keep giving you positive? Oh, no. Yo, we got an A and a B team. Look at that. Negative velocity, then positive velocity, then negative velocity. Cool. All right. We got A and a B. So my derivative is negative until A, which I'll find in a second. And I'll write down the A. My derivative is positive until what looks like 2. I'll call it B. And then it's negative until 5. Yeah, definitely negative until 5. Okay, so I can zoom out. And now we can find these values. Okay, A is 0.14501. So let's save that value. Let's get rid of this value, save this as A. You also copy and paste it. Let's find B. Okay, there's B. Going to save this as B. B equals. Cool. Write that down. So my position decreases, increases, decreases. I'd like you to find all of these, but let's say I didn't care. We'll be able to find it by like subtracting the positions, you know? Why don't we just say the position at A equals my initial position, which was 4. So P of 0 is 4. Is 4 plus my displacement of position, which is accumulating my velocities over times. P of B is that plus A to B. And then P of 5 is that plus B to 5. That's probably easiest to do, but I don't have to like really, I don't know, I'll show you. Look, we already have this value is negative 0.343. Add 4 to that, and I get my position A is 3.656, which is just a little left to where we start. And then we're going to increase. I'm going to copy this and paste this and add A to B. Might be easier than like copying down that number and using it. So that's 12.665, which means if you subtract these two positions, you'll get how much you increase, or you can see that we increase 9.009. If we understand that, you can undo that. It's really easy to undo. And then I'm going to add my integral from B to 5. So one thing that you can't have is like copying and pasting this number down very easily, whereas in the calculator it does copy down very easily. And if you wanted to, you could see, all right, if I get to a position of 12.665 and I go all the way down to -9, I bet you the accumulation of my velocity from B to 5 is going to be like close to -13. There you go, -13.574. Remember, this is just my meters per second over second. It tells me my meters that we've changed, the displacement. So that goes with that, that goes with that. That's how much we go up and down. Cool. Oh my gosh. I totally screwed up. I just wasted a lot of time there. Whoops. What happens if I give you... I mean, that's still true. Erase that. I'm a little off. My position at time 4. Instead of adding the displacement, I need to subtract the negative displacement to get the position in the past. I'm doing a horrible job at explaining this. I hope you guys are picking this up. I hope hope you're not like, oh gosh, Mr. Messer, what's going on here? I don't understand a single thing that's going on. Let's just talk about a scenario. If you have a position at time 0 is 5 and a position at time 5, which is 3, you know that over those 5 seconds, you've decreased 2. Cool? So like, boom, these 3 work together. We can see this plus this equals that, right? Well, go backwards. If I have these two numbers and I need to go back to that, instead of adding the -2, I will subtract the -2, make it a +2 to know I have to come from 5. So let's work our way backwards. What I was supposed to do, which I wasted 5 minutes doing, is say, well, P of 5 is 4. P of B is 4 minus the accumulation from B to 5. P of A will be P of B minus A to B. You could also go from 0 to B. P of 0 equals P of A minus the accumulation of P prime. I don't know why I'm putting V here. I should put P prime. I'm really off. P prime. It's because I'm doing it in my calculator, you know? I guess that's why, because in my calculator I'm using that. But I meant P prime. It's very important to say you're accumulating your derivative, your y's per x over your x's, your meters per second over your seconds to get meters. All right. Now let's get the answers. Okay, 5, 4 minus b to 4. So I will decrease a lot, which means I will come from here. I will then also subtract integral from a to b. Which is 8.565. Then I'll also subtract the integral from 0 to a. Then I get 8.909. Now, does this make sense? Well, zero to a of v of t dt is negative 343. Does it make sense that I start at 8.909 and then I get to 8.565? Yes. A to B, 9.009. Does it make sense that I get from 8.565, add 9.009 and get 17.564? Yes. B to 5. Does it make sense that I get from 17.547 and I end at a position of 4? Checks out. This number, this number, this number, and these numbers make sense. Okay? That stunk that I had so much to do, but that's okay. All right, can I get, what am I doing? I'm always giving you these positives and negatives. It's not always going to be the case like that. All right, t squared cos t plus 2. Positives, negatives. I mean, it's the same, like, I don't know. It's not always this, right? My bad. My derivative is positive until this value a, and then it's negative. We're going from 0 to 3. I have my position at time 3. My position at time 3 is -2. I need to find my position at a and my position at 0. I know that I will decrease from a to 3. So if I end up at a position of, it's probably best to go in order here. Maybe let's go backwards. I will have to decrease to get to -2. Whatever amount that I decrease, I'll need to subtract that decrease, kind of go opposite. So I'm going to go P of 3 minus the negative accumulation of P prime. And then for P of 0, same thing. I will subtract this positive number from P of A. Make sure the numbers work. Make sure you actually do this yourself. Close off this, close off this. I have one A value. The A value in this case is 2.06103. Cool. So let's get A involved. Let's actually go from A to 5, A to 3. I end up at -2, but I subtract that. Let's make sure this is labeled A. And there we go. This position is 1.116 because I decrease 3.116. Cool. So 1.116 minus 3.116 gives me -2. And then I take that -2 minus, and I will also subtract my integral from 0 to A. Or you could just say, all right, instead of subtracting A to 3, you just go all the way from 0 to 3. And you get that same value, -3.047. And that's because the integral from 0 to A is 4.164. And if you look at 0 to 3, you can see it's 1. This is the 4.164 minus the 3.116. That means like I end up 1 to the right of where my started. Look, I started at -3. I ended up at -2. So it all works out. And that's the idea behind quickly. How did my position change? Without doing a full sign analysis, you know that if you just accumulate your derivative, meters per second times the seconds over the interval of seconds, you will get how much your position changes. It will incorporate any positive velocities, any negative velocities. It'll incorporate any movements to the right, increases in position, any movements to the left. It's overall change in position. So, you know, sometimes you don't want to do a full sign analysis. Sometimes you just want to figure out, like, what is the change? If I got t to the 2/3, cosine t plus 2. Cool. Overall, I ended up left 2 of where I was when we had time 1. So minus 2.040. Again, and it's about that triangle of numbers that work together, which is going to be important for next class, that if we knew the position at time 1, I'll just write it down without the sign analysis. If I knew the position at time 1 and I knew the position at time 8, I know that they would be 2.04 away from each other. If I have this value, I would subtract this value to get that value. If I have that value, I would subtract the negative that to get that. So add it as a positive. So it's the whole, this minus this gives me this. This plus this gives me this. This minus that gives me that. They all work together. Cool. So that's the idea behind this guy. Make sure you write P prime equals V, or if you just accumulate V. Understanding you're accumulating a derivative, you're accumulating a rate of change, you get overall original things change. I think it's so much quicker. Your position at the 9th second, so P of 9 is 16 more than P of 1. What is P of 9? I don't know. What is P of 1? I don't know. But I know that P of 9 is 16 more than P of 1. Or I ended up 16 to the right of where I started. So that's a good idea here. I don't want to say this. I just want to say P of 8 is 2 less than P of 1. You know, that's the idea. We ended up 2 to the left of where we started. All right, and like we realize that relationship holds. We don't need a full sign analysis like we did on page 1. If you have a position, you want a future position, and you have how the position's changing, you could be just like, okay, cool. My position at my 4th second, I mean, you could just like go ahead and accumulate. Like, maybe it's better. I think a lot of people feel better of like, okay, what do I get if I accumulate this velocity from 2 to 4? And for next year, guys, I got to make sure we have some negatives to positives. So we got 40 e to the negative t sine t minus 5. We're going from 2 to 4. I get negative 8.148, which means my position at 4 is 8 less than my position at time 2, which means if I have my position at time 2, I will take my position at time 2 and I will add this negative 8.148 value to get my position at time 4, or I do this value 3 plus that value to get negative 5.148. Okay, let's see these 3 numbers work together. P of 2 is 3. P of 4 is negative 5.148. The accumulation of P prime is negative 8.148. Let's see how those 3 numbers work together so that we can go forwards or backwards. This position plus the change in my position gives me my future position. This minus the negative 1 gets that. This minus this gives me that. That's actually calculus. We'll see next class. Cool. Same deal. Let's find the accumulation from 0 to 3. Why 0 to 3? Because I have my position at time 0, and I want to know my position at time 3. I can't go backwards. Cool. 1.0478. So my position at 0 is negative 4. My displacement, my accumulation of P prime is 1.047. Add that to get your position at time 3. And for a free response, they would want you to do some acknowledgement that you've accumulated your velocity. So this 1.0478 needs to be written down. And you need to have the idea of you took that and added -4 to it so that you got that value. Okay, we're going backwards. Great. Now I have my position at time 6 is 3. I want to know my position at time 0. I will be able to find the accumulation of my derivative. Well, you're going to subtract to go backwards. If this is a negative number, that means you are going to decrease to get to 3. We need to increase to come backwards, or vice versa. So make sure that makes sense to you. There's ways to get around this, which we can talk about, but I don't want to do it yet until we really are comfortable with this. But maybe some people are going to discover the idea of what if we accumulate going backwards? You know, the idea being, if anybody's paying attention, yes, we can go from 0 to 6, but what if I go from 6 to 0? Why is that negative where this is positive? It's kind of like the idea of you're accumulating it going back in time versus going forward in time. Right now, we're accumulating going forward in time because it makes sense with our understanding of things from left to right. We know we have to take 3 and subtract this to get this. This plus this gets that. Make sure you show all of this work. You could say P of 0 equals P of 6 minus your accumulation from 0 to 6 of P prime. You could actually say P of 0 equals P of 6 plus the accumulation from 6 to 0. If you add it going backwards, it kind of gives you the change from 6 to 0, which is kind of cool. That would be like that idea. All right, so I have my position at time 4. Just make sure we understand that, like, we probably need to write that x of t equals p of t. My position at time 4, I'm trying to find my position at time 1. I am going to look at t sine t, look at it from 1 to 4. I will increase this much. So I increase to get to -2. I must be coming from like -3.5. How to get that, make sure it makes sense to you, is to subtract, make sure the numbers work out, and we do the whole P of 1 equals P of 4 minus the integral from 1 to 4. Let's just get our answers quickly. Going back in time, I'm adding 5.845 to get to 5. I must come from there. Makes sense. And here. Two to four. Since I ended up at -4, I must come from a higher value so that I subtract 11.97. So if I subtract that negative, I get that I must have come from 7.978 because the accumulation from 2 to 4V was -11.978. That is how much my position decreases from 2 to 4, and I get great. Do velocities. Should I do V1? Does that work here? Oh, nice. Then I could do V sub 2. Do a sub with a shift and then the minus sign. If you want to do f of x, g of x, you could do that. I kind of like this. Cool. C V sub 2. Or you could literally do this as VA because it's just VB and this is VA. Yeah, there you go. Look, exactly what you have written. You can write it down. Okay, cool. Well, let's do an analysis of the derivative of A. So we can see over the course from 0 to 5, oh gosh, it changes sign twice. It's positive until A, it's negative until B, and then it's positive. Let's store those A and B values. I'm going to store this as A and this is B. Cool. That way, if I use A and B, it's going to be for this guy. The particle B, 0 to 5, is same deal. It's negative, positive, negative. So we got these values I'll call C and D. So let's store this as C. Let's store this as D. All right. Don't move any of the sliders. That's a little bit dangerous. My position of particle A at 5 is 3. Great. Position of particle B at 0 is 3. Okay. I am to the right of the origin. My position is decreasing, so I'm moving to the left. Let's find the position of particle A at 0. Well, I'm going to take the position of particle A at 5, and I'll subtract this entire displacement, not worrying about any sign changes or anything. I'm just going to go from 0 to 5 of A. I can see overall I ended up to the left of where I started. Should kind of make sense. We have a lot of negative area between A and B. So that's cool. So if I do the position of 3 minus that, I get my position of A at 0 is 12.218. Okay. So I have 12.218 and my position is increasing. I have a position of particle B at 3 and my position is decreasing. So if you think about it, I'm to the right, moving right. This one is to the left, moving left. The answer is away. Particle A is at 12, moving to the right, position increasing. Particle B is at 3, position decreasing. They're moving away from each other. Okay, what about t equals 1? What did I say C and D were? Should have written that down. Oh, shoot. 0.145. And D is 1.989. Okay, so that means my derivative at 1 of particle B is positive. So that means at t equals 1, I'm moving to the right. It's good to know. Go over here. So position's derivative at 1 is positive at t equals 1, which means I'm moving to the right. I need to find said position. So PB of 1, I'll start with the position at time 0 and I'll add my displacement from 0 to 1. This will incorporate all the positives and the negatives, the increasing and decreasing. I don't want to split it up anymore, though I could. It's just going to be a little bit more efficient. So I'm going to go from 0 to 1. That's 4.833. I started at 3, so I get 7.833. Who made this homework? Out of my face. Okay, cool. So I am at 7.833 moving right. Let's find the position of particle A at 1. I mean, I have this nice number, but I also have that number. It's up to you. We do have this position, which is funny because you could actually add from this position 0 to 1, and you get that you are at 14.457. That's an option. You can do P of 0, which you found, plus your accumulation of your derivative. Or you could say our position at 1 is the position at 5 minus the accumulation from 1 to 5. Let's try that. Let's go 1 to 5. And we have 3, and then we get that exact same number, 14.4577. So you saw like those two different ways to do it. You can either go all the way back to zero and then go from 0 to 1, or we can just go straight to 1. What was this time up here? 2.061. So that means I'm moving to the right. P prime of A at 1 is positive. So I'm moving to the right. So this is a horrible question. They're moving in the same direction. Away from the origin at time 0. Particle A at time 0 is located at, we found that earlier, 12.218. And it's moving to the right. So its position is increasing because P prime of A of 0 is positive. So that means it's moving away from the origin. Particle B, its position at time 0 we found, was 3, and it's moving left because the derivative of the position at time 0 was negative. So that means it's moving towards the origin. And great. I'm not doing the last page. And now I give you graphs of velocity with the accumulations. This is easy. What is the displacement of the position of the particle? How much does the particle change its position from 0 to 6? Well, it goes right 5, left 3, right 1. You could just think about it as accumulating all of your derivatives, and you get 3. So it ended up 3 to the right of where it started. We know the position at time 0 is 2. If I want to know the position at time 3, well, my velocity we can see is positive. It means my position increases. I accumulate my derivative to figure out how much I increase. I go from 2, I add 5, I have 7. I hope we understand this. I feel like I'm kind of rushing. Um, P prime, maybe we'll do it all up here. I feel like I'm rushing. I hope you guys are okay. P prime, shown here, is positive until 3, negative until 5, positive till 6. Positive, negative, positive means my position is increasing, decreasing, increasing. My accumulations of my derivative are listed, which tell me how much I go up or down. It's important, but it's worthless to find future positions without a known position, like the idea of finding C. My position at 0 is 2. My position at time 3 is 7. My final position at time 6 is 2 plus 3, which is 5. Or you could say I went from 2 to 7 to 4 to 5. Ooh, I know my position at time 3 is 2. So I got 0, I got my derivative is negative until 1. It's positive until 3. It's negative after that. I can see my position decreases, increases, decreases. I can see the accumulation of my derivative is minus 2 plus 6 minus 3. If my position at time 3 is 2, that's my position at time 4, negative 1. It's my position at time 1, negative 4. It's my position at time 0, negative 6. No, negative 2. Negative 2 minus 2 is negative 4. Negative 4 plus 6 is 2. So I can subtract a negative, which is add. We're good. Over the entire interval, I displace 1 from 0 to 4, accumulating my velocity. We get a total of 1. Left 2, right 6, left 3. Position of 0 is my position at 3, and then I subtracted my displacements from 0 to 3, which is why I subtracted 6 and I added 2. 2 minus 6 plus 2, or 2, 6 minus 2 is 4. So 2 minus 4 is negative 2. Why don't I just go from my position at time 0 and add 0? No, I already have 3. My position at 4 is easy to find. It's my position at 3. Then I add the accumulation from 3 to 4. So the accumulation is minus 3. So that's why I get a negative 1. And we'll finish off. I'm not going to show, I'm going to show all the work that you need to show. All right. Peace out, B's, C's, and D's. I didn't even need C and D. I didn't even need A and B. It's crazy. 1 plus 2 sine t squared over 2. A. Integral. The position of the particle is 2 at time 4. At time 4, is the particle speeding up or slowing down? Okay, at time 4. I'm going to go to t equals 4. Does that work? Nah. I got to go to x equals 4 to look at this point right here. This is the point. My velocity is 2.978, which is greater than 0. So my velocity is positive, but I can see my velocity is decreasing. P prime is decreasing. Let's do it all quickly. Say my velocity, or P prime, is positive and decreasing. Therefore, we are slowing down. If you want to say V and A have opposite signs, great. So here's my velocity that's positive and decreasing. Find the times in which the particle changes directions. That's easy. That's when our derivative is 0. We are looking from 0 to 3. So let's go to 0 to 3. Make sure we go from 0 to 3, not further. And my velocity changes sign at 1 point. T equals 2.707. Justify your answer is it's when your derivative changes sign. Literally just leave it at that. Make sure you put P prime equals V somewhere. This is like P prime is what we use in class. So your velocity changes sign at that location. What is the position of the particle at time 0? Easy. My position at 0 is equal to my known position. And since I'm going back in time, I'll have to subtract the displacement. And I'm good. Displacement from 0 to 4 is that. So that means I increase 5.815 to get to my position of 2. So I'm going to have to subtract that from 2 to know that I start at a position of negative 3.815, so that I can then increase 5.815 to end up at a position of 2. Negative 3.815 plus gives me to that 2. All right, so what was the position? 2? All right. Dude, that was a free response question. Like, piece of cake. There's probably a part D somewhere that we haven't done yet, but like, we're going to see. We're going to be very, very, very much prepared for AP Calculus motion free response questions. All right, that was a fun video. Peace. It was not a fun video. I did not have that much fun, but it's nice to be in the sun, so that's good. We got that going for us. Peace.